Okay, in this video we're going to be doing Calc AB problem set number 18. There's a link to the problems and a playlist of all the problem sets in the description below. And let's get started. Using a calculator, apply the mean value theorem on 1 to 6 for the function f of x equals the the quantity x minus 2 over x plus 3 times cosine of 2x times the quantity x cubed plus 1. So this is like an exercise in correctly typing that into your calculator and then using your calculator to solve this. So first of all, I always like to justify that you can use the mean value theorem because sometimes you need it, sometimes you don't, but it's never wrong to do it. So I'm going to say f of x is continuous on the closed interval from 1 to 6 and differentiable on the open interval from 1 to 6. F of x is not differentiable or continuous, obviously. It's not continuous and therefore not differentiable at -3, but that's not on the interval, so not a problem. So mean value theorem does apply. So what does the mean value theorem say in this instance? It would say that f prime of c is equal to f of 6 minus f of 1 over 6 minus 1 for some c between 1 and 6. There might be 10 values. There might be only one value. It doesn't matter. We are guaranteed at least one value. So with that in mind, I got to do this on a calculator, so I'm just going to show you the screen. I did this. I defined the function, then I asked the calculator to solve. So I have a CAS calculator, and that's how I do this. There's plenty of videos of me doing that if you're interested in learning how to do that and you're not sure. It does give you like a lot of solutions, and it also warns you that there might be more solutions, so I'm not really happy about that. I scrolled through and I found the one that's between 1 and 6. So C is approximately 4.985. I don't like it when it gives me that warning, and I usually then will switch over to just graphing. So here's a picture of that. What I did was I graphed the derivative. I also graphed f of 6 minus f of 1 over 6 minus 1. I didn't calculate it. I just like typed that in. F of 6 minus f of 1 over 6 minus 1. And then I intersected those, and you can see it's the same x coordinate, which is what we were expecting, but it's a little safer because that doesn't give you the warning that like, hey, there might be more solutions. All right, new problem. Given that f of x is differentiable and the table of values below, all right, so we have a table. We want to prove that f prime of c equals 0 for some c between 2 and 10. My advice for proving that the derivative is equal to 0 is always look through the table and see if you can find the same y value twice. If you can find the same y value twice, then the slope of the secant line through there will definitely be 0, and that'll be where f prime is 0 by the mean value theorem. So I am going to use mean value theorem, so I'm going to just like set up overall that I'm allowed to do that. I'm going to say f of x is differentiable, therefore f of x, or that implies rather that f of x is continuous, therefore the mean value theorem applies. So I've set it up. Now I know that at 2 and 10, f of x is 3, which means if I use 2 and 10, I will definitely get a slope of 0. Mean value theorem guarantees that f prime is equal to 0, so let's do that. By mean value theorem, f prime of c equals f of 10 minus f of 2 over 10 minus 2 equals 0 for some c element of 2 to 10. It's like a little disappointing, but like that's it. That's how the answer goes. All right, prove that f prime of c equals -1 for some c between 2 and 10. This is kind of like, there's a bunch of ways you can do this, but we don't know that this function is twice differentiable, which means we don't actually know if f prime is continuous. So I don't want to try to use that approach. What I'm going to do is I'm going to search through the table and try to find a slope of -1. So they don't need to be consecutive. So like you just kind of like go through and check. Like we already know 2 and 10 is not it. 5 to 10, you get -5 over 5. You get -5 over 5. Actually, that's the answer. From 5 to 10, there you go. We will get f of 10 minus f of 5 over 10 minus 5. And then that's 3 minus 8 is -5 over 10 minus 5 is 5, so a -1 for some c that's between 5 and 10. And then again, this is by the mean value theorem. So we want to like say why this is true. Even though we said the mean value theorem applies, like you got to say that you're using the mean value theorem. All right, one more problem. I seem to like making the second derivative the last problem of problem sets. That's an interesting trend. Find the second derivative of y equals sine of 2x e to the 3x. All right, this feels pretty straightforward. So here goes. So dy dx is first derivative of the second. Don't forget the chain rule. So it's going to be 3 e to the 3x plus second e to the 3x. Derivative of the first, don't forget the chain rule, 2 cosine of 2x. And then you almost always, when you're finding second derivatives from the original function, you definitely want to clean this up. So I'm going to clean it up a little bit, take out an e to the 3x. It just makes it so that I can use the product rule again and not have to use two product rules and have to clean that up. So here goes. We're doing it again. We're going to go first, e to the 3x, derivative of the second. Don't forget the chain rule at any point. So it's 3 times 2 cosine of 2x, which becomes 6 cosine of 2x. And then it's 2 times negative 2 sine of 2x, so it becomes minus 4 sine of 2x. So that's first derivative of the second. Plus second derivative of the first, which is 3e to the 3x. And like, I don't know, depending on what you're doing, you might be able to just leave this. You can definitely take out an e to the 3x, and then there's like, just clean it up. You should get this. E to the 3x quantity 12 cosine of 2x plus 5 sine of 2x. If you're real, like, I don't know, I'm just going to say weird. You can actually combine 12 cosine of 2x plus 5 sine of 2x, I think, if you wanted to, but like, don't do that. Okay, so I would leave it here, and I hope you found this helpful, and good luck.